When we talk about the strengths of acids, we can incorporate the ideas of the conjugate pairs that we just looked at. We're going to see that if we were to kind of qualitatively assess acid strength and kind of rank acids from strongest to weakest, and if we were to make that list, we could point out certain conjugate bases, right? Certain acids have conjugate bases. So if we go ahead and look at that table, which we don't need to actually look at, there's an important trend that comes out. And that trend tells us that the stronger the acid is, the weaker the conjugate base is. And that's going to be a very, very important consideration for us, especially when we go into organic chemistry. When we look at how strong an acid is, we will also get information about its conjugate base. So whatever your acids happen to be, if you're comparing two acids, if one of them is stronger than the other, the conjugate base, say the first one is the strongest, acid 1, conjugate base 1 will be a weaker base than conjugate base 2. So, with that in mind, we can say a couple of things. For our strong acids, as you remember, the strong acids were the halogen acids except for fluorine, sulfuric, nitric, and perchloric acids. So I'll just write those out. HNO3, H2SO4, HClO4, HCl, HI, HBr. These are our strong acids. For our strong acids, remember they're called strong, differently for stronger, but they're called strong because they dissociate completely. They're strong electrolytes. When we're talking about stronger, they can be weak acids. We're just comparing their relative strengths. So, for strong acids, the conjugate bases are negligible bases. Meaning that if we say HNO3 plus water turns into H3O plus and nitrate, we see that this is not really an equilibrium. The equilibrium so favors the products that we don't really see the reactants at all. We don't see nitric acid as such. We see H plus and nitrate in solution. So we can go ahead and get rid of this equilibrium arrow and instead put in a regular reaction arrow that we're used to seeing. This is effectively irreversible because the conjugate bases of these strong acids, because they're strong acids, the bases must be extremely weak, so weak as to be negligible. So we don't ever see chloride as a base, or iodide as a base, or bisulfate as a base. The conjugate bases of these acids are negligible. For weak acids, however, which is the majority of acids, right? It's every acid that's not a weak acid, or a strong acid rather. For weak acids, the conjugates are weak bases. So, weak acids, weak bases, they go together. So something like acetate, or I guess we need acetic acid, plus H2O. This will definitely be in equilibrium because we'll have acetate and hydronium. And in fact, this equilibrium lies to the left, right? Its K is going to be quite small. In fact, it'll be somewhere around 10 to the -4 power, thereabouts. So we have quite a small equilibrium constant for this reaction. Very much favors the reactants. Remember, small k favors reactants, big K favors products, just in your distribution. The Ks for the strong acid reactions are very much product heavy. They're very large values. However, the K for weak acids will be very small. Excuse me, I'm going to sneeze. Goodness. Okay. And then the last one, we don't really have a category called negligible acids, but let's make it up. For negligible acids, not really a category we have, but we'll just put it out there. For negligible acids, the conjugate bases is strong. So, for example, if we have water going ahead to give us, with say, we'll put it with acetate. Water is such a weak base, but I'm sorry, a weak acid. So we can kind of consider it negligible. Notice what happens in solution. We end up making our acetate plus OH minus. The conjugate base here is strong. OH minus is a strong base. So our conjugate base here for this negligible acid is strong. So extremely weak acids have very strong conjugate bases. So like water. Water's conjugate base is very strong. Water's conjugate acid is also very strong. And so we're going to see these patterns also exist for bases. Again, we always frame everything in terms of acids. That's just convention. But it's the same thing here. If we just switch the words acids and base, right? For our strong bases, sodium hydroxide, for example, the conjugate acids are negligible acids, like water. So NaOH, strong base, conjugate acid is water, negligible acidity. For now. We'll see when we get to organic chem, there's much better bases than hydroxide, but that's not now. Okay, and then for this as well, for weak bases, the conjugates are going to be weak acids. So for acetate, a weak base, your conjugate acid is acetic acid, a weak acid. So again, this all applies for bases as well. And then finally, for negligible bases, the conjugate base, for negligible bases, the conjugate acid is strong. For example, chloride. Chloride is not acidic at all, but its conjugate acid, it's not basic at all. I can't even switch the words properly. Its conjugate acid is strong. So all these terms still apply for bases as well. Just switch the words and don't get confused like I did. All right, the whole point of this, by the way, is that reactions and the extent of the reaction, if it's an equilibrium situation, like where is that equilibrium going to lie? Is it going to favor the products, favor the reactants? Reactions can be predicted as the following. The stronger acid, meaning whatever in your system, if we're looking at water, acetate, acetic acid, and hydroxide, the stronger acid will always donate its proton as much as possible to the base. And that means that your stronger acid is always going to be the small side of your equilibrium constant. So that means that if acetic acid here is our strongest acid of all these things here, acetic acid is the strongest acid, the equilibrium will lie away from that. The equilibrium will be on the other side. So indeed, we're going to see that water and acetate is going to be mostly what's hanging around in this collection of molecules. The equilibrium will favor the other side, meaning that the wherever your acid happens to be, the equilibrium will be on the opposite side. So equilibrium will favor side without the strong acid. Without the stronger acid, I should say. So we can say, qualitatively speaking, predicting this reaction, that if we take a look at all of these molecules, the strongest acid here is going to be acetic acid, right? We have water, acetate, acetic acid, hydroxide. Acetate and hydroxide are not bases at all, or they're not acids at all. Water is a negligible acid. Acetic acid is going to be our best bet here. And so, with that, we're going to see that because acetic acid is on the right in that equation as written, the equilibrium will lie to the left. So it'll always be favoring the opposite side as where your strong acid is. Okay, so it's always going to be favoring that sort of transfer as well. And so again, we kind of frame this in terms of acids, but again, we have that same idea of the base would work as well. So you can frame this in terms of the base. It technically at this point, then we would need to compare the strengths of your strongest acid versus your strongest base. What's the strongest thing there? But that'll go a little bit more complicated. That'll go more towards something we're going to look at in the next couple of sections. So with that, that's it for this video. And in the next video, we'll talk more about this idea of equilibrium in acids.